Good evening, good afternoon. My name is Valentin Khokhlov, and it's seventh issue of my investment club, seventh meeting. As I promised in August, that we will talk about such a risk measure called VAR, or value at risk. And as I see, there will be 2 or 3 meetings dedicated to this risk measure, as this topic is quite complicated. And today we will start, and then we will continue with the more sophisticated aspects of using this risk measure. And we'll start with two guys here. Nassim Taleb and Philip Jorion, and Nicholas Nassim Taleb is a famous trader and famous author of the Black Swan, the book and the concept, where he criticized risk management, quantitative risk management, and especially value at risk measure. And another guy is Philip Jorion, a famous researcher and the author of Financial Risk Manager Handbook, which is the basic source for financial risk manager certification, the leading professional certification in quantitative risk management. And Philip is a strict advocate of VAR. And so we have quite a conflict of two approaches, Taleb with Black Swans and Jorion with VAR, and we'll speak about VAR first. So value at risk, or VAR, is such amount of losses that the probability of getting a larger loss does not exceed a small pre-specified amount. So you set a small pre-specified probability, and you get this VAR as the amount of loss, so that the probability of getting larger loss is smaller than the probability you set. What is important about VAR? Why it became so popular? First, it's a monetary measure, so it's measured in money, in US dollars, for example, and not an abstract unitless measure like standard deviation or beta or some other measures, because what is standard deviation? You get standard deviation of returns. How you measure returns? Returns is unitless. Basically, you can express it in percent, but it is a ratio of profit to initial value of the portfolio, so it's unitless. And standard deviation also is unitless. So you get some amount, some number, some percentage, and what does it say? The same is beta, which is regression coefficient, also unitless. So what does it measure? It measures some sensitivity about how much you can earn or lose based on this risk measure. You can say VAR is measured in US dollars, or another currency, so you can use it directly to assess your potential losses on a position or on a portfolio. What is also important, standard deviation is not specifically tied to any direction. So it measures the deviation from the mean. Deviation downside, maybe downside deviation to the losses, or upside deviation to the profits. It does not matter for the standard deviation, because it accounts for all deviations. Well, there is semi-standard deviation, or downside semi-standard deviation, which only accounts for the downside deviations, which is to the losses. But it's not very often used. So value at risk only considers losses. or only considers one tail of the distribution, and we use a tail which corresponds to losses. In case of returns, it's called left tail, and we'll see why it's in the left. So it's not only monetary measure, it's also downside measure. Secondly, it's probabilistic measure, because unlike standard deviation, which works for all distributions, and it does not depend on the distribution, VAR ties probability to the amount of losses, and it requires some distributional assumption. So you need to assume some distribution in order to relate those two figures. So value at risk only works for a particular distribution. It's very important. We'll see how it will affect the black swans for some distributions. And third, value at risk indicates some threshold. It says nothing about how large your losses might be. It says only that the losses are larger than this threshold with this probability, but they may be a bit larger, or they may be a huge deal larger. You cannot say the magnitude of losses, you only see their minimal amount. So let's see how it looks like on some graphs. So you see here the distribution of returns, this bold green line. So here we have 0. 0 means no profit, no loss, so you get the same amount of money. You have the expected return. We hope it's positive, so you have some expected positive return, but you also have some values with some probabilities that are below 0, which means you earn less, you end up with less than you invested. So this is the area where you have losses, and it's to the left of 0, so it's the left tail. So basically that's why we call it left tail area, left tail probability. And for some probability at level alpha, you get huge amount of losses here in this area that is highlighted. So basically we are interested in this area of the left tail. If we get the definition of VAR, it's the amount of loss, so that the probability of getting loss larger than this level is less than alpha. Loss is initial value of the portfolio less ending value of the portfolio. So if your initial value is larger than the ending value, you get loss. If this loss is quite larger than L, you end up here in this area. So we are interested in this amount. We set the probability alpha. We're interested in what is the level, is a threshold, is this level that corresponds to this left tail. So we divide everything by P, initial value of the portfolio P with index 0. So if we divide this amount, we get the loss per every dollar of the portfolio, which is the opposite value to the return on the portfolio. And if we divide L, this level, VAR level, by initial value of the portfolio, we get what I called small v, or relative VAR per $1 of the portfolio. And here, if we multiply this expression under the probability, if we divide it by -1, we get this expression. We have probability of return that is smaller than -v. And this probability should be alpha. So here we have this expression which is equivalent to the definition of the value at risk. And we can calculate the value at risk based on this final expression. How we do it? If we have some sample of returns, so it's called empirical value at risk. We have sample, let's say, of 1,000 daily returns. We sort them in the ascending order from smaller to larger, and we take element corresponding to alpha multiplied by n. If we have 5% var, we multiply 5% by 1,000, it's 50, so we take 50th element of our sample, and it's our empirical var. Or if we use Microsoft Excel, we use percentile function which calculates this percentile automatically. So basically we have 50 elements under this threshold, 50 elements in our left tail, which corresponds to 50 losses larger than var. So you have this definition of var that it holds basically. By the way, often you can face the 95% var or 99% var. It's the same as here 5% var or 1% var. Why? Because I use the distribution of returns, and I'm interested in left tail, and in the left tail we have probabilities like 1%, 5% and so on. Some people use the distribution of losses, and they are interested in losses higher than some threshold. So they use the right tail, and in the right tail you have probabilities like 95%, 99%. So 95% probability for the distribution of losses correspond to 5% probability of returns, 99 to 1%. So it's the same. And basically you only need to know you are working with the left tail and use 1% or 5%, or you are working with the right tail and you use 95%, 99%. It does not matter, but some people use the second notation. I will stay with my notation with like 1% or 5% var. So the other approach is to use theoretical, sometimes it's called variance covariance var. We don't have some historical sample, so that we need to make some assumption. We assume that our returns will adhere to some distribution, normal or some other distribution, doesn't matter, but we need to make some assumption. We start with the formula on our previous slide, that the probability of returns lower than minus v equal to alpha, and we use the so-called inverse cumulative distribution function, or which is the same, we use the quantile function. It's called f minus 1. And by definition, this v minus v in our case equals to the quantile at level alpha. So it's the definition of this inverse cumulative distribution function. So we can easily calculate if we set the alpha at 5% and we use this quantile, 5% quantile of the distribution, which depends on the distribution we have chosen. Sometimes we can use a standardized distribution. What is a standardized distribution? We use a distribution, a random value. We center it at 0 and we use the scale parameter of 1. So if we have a generic distribution with two parameters like center and scale, we just subtract the center and we divide by the scale, and we get the standardized distribution. And the standardized CDF, or CDF for standard normal distribution, is called phi, Greek capital phi. And in Microsoft Excel, this quantile function for the standardized normal distribution is called norm as inf. So it's easy to calculate the quantile for this standardized distribution, and if you need a particular normal distribution, you then multiply by sigma, by standard deviation, and you add the mu, which is expected value. So basically you can easily calculate the theoretical value at risk. How the black swans are related to this concept. So let's ask the simple question. Let's suppose we are interested in learning how often we can face very large losses larger than 6 sigma. So it's, by the way, Nassim Taleb, as far as I remember, uses this 6 sigma case in his Black Swans book. So normal distribution, if we use this formula for this quantile function, and we just calculate this amount, the probability in the left tail corresponding to this 6 sigma threshold, this probability will say that it happens once in 3.5 million years. So virtually you face no such loss ever in your life. Once in 3.5 million years, and we are speaking of daily returns, not annual returns, daily returns, once in 3.5 million years. But in fact, you can face such losses once in 3.4 years. So if you assume your returns are normally distributed, your daily returns are normally distributed, you have huge 1 million times underestimation of your risks. That's a black swan, what's called black swan. You calculated your risk measure, you do not expect such magnitude of losses, or you do not expect losses of such magnitude ever, but you face them in practice quite often. If we move a bit to the right, if we use 5 sigma instead of 6 sigma for normal distribution case, it says you can face such a loss or a greater loss once in 16,000 years. Again, virtually you do not face such a loss ever if you believe in normal distribution. But actually such losses, such extreme losses happens once in 2.2 years. So every 2 years you face them. If we move to 4 standard deviation, to 4 sigma, the normal distribution says, well, you can face such a large loss once in 120 years. So, well, probably not in your lifetime. But actually, you see them every year, specifically, to be more specific, once in 0.93 years. So every 11 months you face such a large 4 sigma loss. So basically it says that you cannot use this value at risk framework with normal distribution for daily returns. Does it mean that you cannot use var in all instances? It turns out that no, you cannot make such conclusion, because there are different probability distributions, not only normal. The fact that the risk managers did use only the normal distribution in the beginning of 2000s, before the financial crisis, it was criticized by Taleb, and he was right with his critique of the normal distribution used in VAR framework. But actually we can use other distributions, and if we consider Dow Jones Industrial Average, you see this bold, solid bold line. It's the actual distribution of daily returns for Dow Jones. And you see here the dotted line. The dotted line is a normal distribution, and you see the significant underestimation of risk in this region, in this left tail. The normal distribution goes virtually to zero, but the actual frequency of getting such losses is far from zero. It's relatively far from zero. It's not non-zero. But if you consider students' t-distribution with 3 degrees of freedom, or you consider the Laplace distribution. Laplace distribution is denoted with a solid red line, and the students' t-distribution with 3 degrees of freedom is denoted with a dashed blue line. You see their estimation of left tail risk is much closer to the actual amount we see from the actual distribution. So basically we have some ways to alleviate this problem, or maybe eliminate this problem, and we will see how it works. So here is the table that summarizes what I have just said. So for Dow Jones, 6 sigma case, 5 sigma case, and 4 sigma case, and you see the amount of years, and you can compare it to actual years. You see this virtually the same goes for S&P 500. I used SPY ETF, which tracks S&P. So here I use SPY ETF, which tracks the S&P 500 index, and you see about the same magnitude of underestimation of risks for the normal distribution, and about the same for General Electric stocks and for ExxonMobil stocks. But if we use students' distribution with 3 degrees of freedom, or Laplace distribution, you see the amount of years on average you can face such extreme losses is comparable. For students' distribution, it's actually comparable to the years we see such extreme losses in practice. For Laplace distribution, for 6 sigma and 5 sigma case, yeah, we have some underestimation, but it's not such a significant underestimation as for the normal distribution. So you see, we can relax this black swans problem if we use fat tails distributions, and we actually should use them instead of normal distribution, at least for daily returns. Here you see some statistics test, distribution tests. First one is Pearson's test, and it's chi-squared statistics. You see huge number for normal distribution. Of course, the normal distribution is a very bad fit. Actually, other distributions are not that great as well, but they are much better. And we have Kolmogorov-Smirnov test, and it's test statistics K. Again, much larger values for normal distribution. They all are not very good fits. Actually, the critical value is well below 2. It's closer to 1 something. But still, you see, student distribution is much closer to this critical value, and Laplace distribution also much closer than normal distribution. So what we can conclude: the normal distribution or Gaussian distribution is a bad fit for daily returns. Do not use it for daily returns. But it's a possible fit for annual returns. Why? We'll see a bit later. Then, if you use the student's t-distribution with small amount of the degrees of freedom like 3 or 4, it's a good fit for daily returns. If we use monthly returns, we need to increase the amount of degrees of freedom, and as you increase the amount of degrees of freedom for students' t-distribution, you go closer to the normal distribution. And the normal distribution is the same as the student's t-distribution with the infinite amount of degrees of freedom. So basically, as you increase the amount of degrees of freedom, you get closer to the Gaussian normal distribution. And if you use annual returns, you need to use degrees of freedom like 20 or something like that, which is really close to the normal distribution. Well, if you use student's t-distribution, it's really good choice for daily returns, but it has some complicated formula, especially for the quantile function. You cannot express this formula using like standard math. So it has no closed formula. If you use Laplace distribution, it's not such a good fit as a student's t-distribution with 3 degrees of freedom, but still it's a pretty decent fit for daily returns. But for the Laplace distribution, you have a very simple formula. You literally can calculate the value at risk using a pocket calculator, and of course you can do it in Excel as well. There are many other distributions. We will not spend time in this issue. We will speak about them another time. We'll address the next topic. You virtually never work with daily returns if you manage portfolios. You work with returns on investment horizon, which is much longer than 1 day. What you can do? You can use a periodic returns distribution, monthly, annual, or for several years, but where you can get such samples. It's not very easy. Actually, it's very difficult to get samples of periodic returns longer than 1 year. Even for annual returns, it's quite hard to get proper samples, long samples. Another choice would be to translate daily returns into periodic return, daily value at risk into the periodic value at risk. How? For the returns, it's easy. You use the compounding. You just use product of sub-period returns. But for value at risk, you cannot use this formula because what will be the distribution of this product? Mathematically, it's very difficult to speak about the distribution of the product. Well, what we can do, we can take the logarithm of both parts here, and we know that the logarithm of the product equals to the sum of the logarithms of its arguments. So we switch from the product to the sum, and it's easy to work with the sum of random values. If we have normal random values, normal returns, normally distributed, this sum will be normally distributed as well. If you use students or Laplace distributions, it's not the case, but there is central limit theorem which says that all the distribution, if you sum up many values, their distribution of the sum will be about normal. The more values you have in this sum, the closer the final distribution will be to the normal. That's why if you use, for example, annual distribution where daily returns are distributed by student or by Laplace, but you sum up them, you get really close to the normal distribution. That's why the annual returns have distributions which are virtually normal. That's why. So we use for value at risk, we need to use, or it's better to use not the standard returns, not the raw returns, but conditionally constantly compounded returns, or logarithm returns. So you take raw return, add 1 and take the natural logarithm, and that's what is continuously compounded return, or logarithmic return. But in order to get value at risk, you need to make opposite translation from the logarithmic space to the raw returns space. You use the opposite function, you use the exponent for such translation. So, and if you need to go from daily returns to periodic returns, and you have some kind of mathematical expectation or mean daily return, you just multiply it by the length of the period, and for the standard deviation you multiply by the square root of the length of this period, and you get the periodic mean and the periodic standard deviation. Well, it's not 100% correct, but it's a good approximation. It would be correct for normal distribution, by the way, but not for other distributions, for identically distributed daily returns. So then you can get the standard formula of value at risk, and you see that the periodic value at risk equals to the daily value at risk multiplied by the square root of the length of period, the same way as you use for standard deviation, but you need to add or subtract, in our case, some additional value which depends on the length of the period and on the mean return, which perfectly makes sense. So periodic value at risk, it says about the extreme losses. But if you have on average positive returns every day, and the longer period you take, the less losses you will get, because this daily positive average return will compensate for such extreme losses over a longer period. And the opposite will be true if the daily return on average is negative. You get worse loss than if you just multiply daily loss by this square root of t. So here we use logarithmic returns and its statistics. Then we need to get back from the logarithmic space to normal var space, and we use exponent here, and well, it's basically easy, but here is 1 minus var, because we deal with the left tail, so we do not forget this minus, and in exponent case we add this 1 minus something. And so we see that this periodic var equals to this daily var, and of course with exponent multiplication is switched to power function, and here we have this exponent of this additional value. So it looks sophisticated, but mathematically it's quite simple, and it's simple to calculate. Does this formula actually work? In the case of 5% VAR and in case of monthly investment horizon, we use this column, actual monthly value at risk, and the second column we have translated from daily value at risk. So we have daily value at risk, and then we translate it into the monthly one. They have some difference, they have some error, but the magnitude is about the same. So actually this formula is not perfect, of course, but it can give you some some assessment of periodic value at risk if you have calculated daily value at risk. So you can translate with some estimation error, but still in most cases you get pretty close estimates of this periodic value at risk. So for different distributions, for three distributions we have considered today. For the normal or Gaussian distribution, in case we have a logarithmic or continuously compounded returns and their means and standard deviations, we have to get back to the row return space to end up with correct value at risk value, and you have this formula, this exponents, and this phi minus 1 degree is the inverse function for standardized normal CDF, which is norm as in Microsoft Excel. For the students T distribution, formula is about the same. You also have this mu, which is expected value for logarithmic returns, and sigma, which is standard deviation of logarithmic returns, and you have this T minus 1, which is inverse CDF for students distribution, but also you need to have this addition because the scale parameter for the students T distribution is not the same as the standard deviation. It has this addition, it depends on the degrees of freedom, but it's simple, it's just the square root, but you need to include it. And this T minus 1, in order to calculate it in Microsoft Excel, at least in the old versions, you need to use so-called two-tailed function, which called tinf, and as it is two-tailed, you just multiply the probability by 2 and you use minus, because this two-tailed version gets the right tail and you need the left tail for our returns distribution. And in case of Laplace distribution, we consider only the left tail, so alpha less than 0.5. And for this left tail, because the formulas are different for left and right tail for Laplace distribution, for this left tail, this very easy to calculate, very easy to use formula, also mu, which is expected value or mean return, and this sigma, which is standard deviation, and alpha. So no strange functions here, very easy to calculate. And finally, what would be the portfolio value at risk if we have some assets in this portfolio? If we do not consider a portfolio as an asset, if we consider portfolio as some set of assets with their own weights, you can calculate the portfolio expected return using the weighted sum of assets return, and you can calculate the portfolio standard deviation as this quadratic form and take square root of it. But mathematically it would not be correct to use it as a portfolio value at risk. Why? Because you have different returns for each asset, you have different returns distributions, and nobody can guarantee you that the resulting portfolio returns distribution will be identical to the distribution of its components. In very rare cases, you can say that all the portfolio assets are identically distributed. Generally, it's not the case. So generally, it's impossible to stay mathematically correct if you just take this formula as if you calculated the portfolio return and standard deviation and then use those to calculate the value at risk of the portfolio. But if we close our eyes on the mathematical strictness, we can use those as our optimization model. We use a utility function like we use in Markowitz model, in Sharpe ratio optimization, and other optimization models which we spoke about on our previous meetings. So we use this non-linear optimization model because of the square root. It's linear, but we can deal with it, we can cope with it, we can get the algorithm and we can calculate the optimal portfolio values. Okay, so what we can get if we use this model? If we use this model, actually we get some var optimal portfolios which are also mean variance optimal, because the model actually ends up with the same as Markowitz optimization model. It works, by the way, it works only for the distributions that have two parameters, mean and standard deviation, or center parameter and scale parameter. But luckily, all elliptical distributions require two parameters. So normal distribution, student's t distribution, and Laplace distribution, they all are elliptical. So you can work with any of those fat tail distribution, I mean student's t or Laplace, using this model, and with some other as well. And so we can get those portfolios which are the same as Markowitz optimal portfolios, so they reside on the efficient frontier and they are quite close to the mean variance portfolio, so-called minimum risk portfolio. Let me show you this figure first. So it's you can see here the left tail of the Markowitz efficient frontier. It's about the same region where there is a minimum risk, minimum variance portfolio, and you see it's the scale is very, very large. So you have this 11.4, 11.5, 11.6 standard deviation, which is very large scale picture, and all those portfolios were optimal for 0.5 probability, for 1% probability, 2% probability, 5% probability var. They are very close to each other, they are very close to efficient frontier. Actually they should reside on the efficient frontier, and only due to some calculation errors and imperfect calculations they are not shown on this blue line, which is efficient frontier. So basically they reside on efficient frontier, they are close to each other, they are close to minimum risk portfolio. If we calculate their investment results, so you have here students t, Laplace, normal distribution, you have 4 probabilities for value at risk. You have daily returns, you have daily standard deviation, and you calculate the model value at risk and you compare to the value at risk you achieve using, if you compose those portfolios, what you would have achieved in fact. They're not the same. Basically, the model is not perfect. But the magnitude, sometimes it's quite close, sometimes it's not very close, but it's not critically mismatch as well. So basically this model works. It will never work perfectly because mathematically you cannot calculate portfolio value at risk using its components in the same way as standard deviation, unfortunately. But with some model error, you can calculate optimal portfolios, and they will not be very far from actual portfolios with low level of value at risk. So basically what we could probably do for value at risk optimization. And we have another risk measure. We will briefly speak of it now. We will speak of it in more details during one of the next of the following streams. This measure called conditional value at risk. It does measure the expected value of losses larger than value at risk, larger than 1. So the mathematical definition, it's the expected value of loss that are larger than var, and here is the formula, quite sophisticated, or it looks quite sophisticated because you have this integral from minus infinity to this var level, and this is for calculating the expected value. So it's not easy to get a closed form expression for this conditional value at risk for many distributions. Only recently myself with my co-authors derived formulas for many probability distribution. It's published in Annals of the Operation Research, and this paper is available, but we'll consider it later. What is good about this conditional value at risk? It's considered to be a coherent risk measure. This definition of coherent risk measure as a risk measure that has several properties, such as it's normalized, so it's zero when you have no risk assets. It's monotone, so if you have one portfolio which is better than another portfolio, its risk measure should be lower. Very important property is subadditivity, which says that if you have you have two assets, the coherent risk measure of the combined portfolio should be not larger than the sum of those of the risk measures of those two assets. Positive homogeneity and translation invariance that basically say if you scale up the portfolio, the risk measure will increase by the same multiple, and if you add some amount of cash to the portfolio, the risk will be lower regarding the amount of cash you have added. But for us, the subadditivity is really important feature, as it can it's not real additivity where you have the risk of the portfolio equals to the sum of risk of its assets. That would be great, but we don't have such a risk measure. But at least it says if you have the weighted sum of the assets, it will provide an upper limit for the risk of your portfolio. So your actual risk will be lower than this sum of individual assets risk, which is good. So for conditional value at risk, you have this property. For normal value at risk, for usual value at risk, you do not have this property, which is quite unfortunate. But still, this good measure of risk, like coherent measure of risk, conditional value at risk, is not so easy to calculate, but during our next meetings we will see what we could do with the conditional value at risk and what how it differs from the value at risk for some asset classes, like not only for equity, not only for stocks like we have considered today, but also for bonds, for real estate, for commodities, even for private equity or hedge funds. Well, quite limited amount of such assets, but still we can check what those two risk measures show us. So I thank you for the attention, and hope to see you again on the upcoming streams where we will speak of conditional value at risk and some other properties of risk measure. So stay tuned and have a good evening. Goodbye.